Here we go. The number of students infected with flu after T days is modeled by this function. Okay, so this tells me how many kids have the flu at any given time. Hopefully I copied that right. All right. What was the initial number of infected students? Now, that number is not in there. You're not going to see that number. You're going to have to figure it out. But you can figure it out because if we're talking about the very beginning, what are we going to let T be? What is the time? At the very beginning, the time is 0. So to find your initial value, you let, I always say X be 0. In this case, it's T be 0. We're going to let T be 0. So when we plug in 0, won't we just get e to the 0 if we put a 0 in there? And what's e to the 0? 1. Anything to the 0 is 1. So our answer is just going to be 800 divided by 50, which is what, 160? So 160 kids.
16.
Oh, 16. Oh, yeah, I lost a 0 in there. Thank you. Thank you very much. 16 kids initially had the flu. Okay, so how do we find our beginning value, our initial value? We let T or X be 0. The initial value is always the y-intercept, always. Okay. When will the number of infected students be 200? When will the number of infected students be 200? So we go back to our equation, and what do we do with the 200? Put it in right here, right? This is how many kids are infected at a given time. So we're going to have 200 equals 800 over 1 plus 49 e to the negative 0.2t. Okay, this is big time math. How in the world do we solve this equation? What do you think? Dan?
Can we graph it?
Oh, absolutely. I mean, we're going to do it algebraically, but you're right. You're right. You could graph this, and if we were going to graph it on our calculator, you could graph 200, graph this mess, and look where they cross. That would absolutely work. We're going to do this algebraically, though. Katie?
Do you multiply this down?
Absolutely. Let's get rid of the fraction. So we're going to take this guy right here and multiply him over here. So that's going to be a distribute. So we're going to have 200 plus, okay, now remember, you're multiplying this over here. So you're taking 200 times 1. Okay, that's 200. Now, what's 200 times 49? I'm not going to trust myself because I'm clearly not thinking straight today. 9,800. E to the negative 2.2t. And that equals 800. Okay, so everybody got that? We're going to bring this over here. Okay, now what do you think we should do? Subtract the 200. So we have our 98,000 e to the negative 0.2t equal to 600.
Yeah.
Divide by the 9,800. So e to the negative 0.2t equals 6 over 98. I know that reduces. Go ahead and reduce it if you want, but I'm going to go to my calculator anyway, so it doesn't matter. What do we do?
Use like the LA.
We got to take the logarithm of both sides. We have to take the logarithm. Now, The logarithm you choose doesn't matter. There are billions of different logarithms, log base 8, log base 25, log base root 17, millions of them. The one that would be the easiest, the most convenient in this problem is the natural logarithm, because the base of the natural logarithm is e, and the problem has an e in it. And the beauty of that relationship is whenever an ln and an e touch each other, they cancel out. They're inverses, so they cancel each other out. So we have negative 0.2t equal to ln 698. Now remember, we ln'd both sides. This one canceled, that one didn't. So t, which is the answer to the question, will be ln 698 divided by negative 0.2t. Divided by negative 0.2, not 2t. T equals divided by negative. I got, what was the question? When will the number of affected students be? I got about 14 days. Anybody else get that? Did you get about 14 days as the answer? Now, if you have an issue with that, we're going to do another one just like it. The school will close when 300 kids are infected. When will the school close? Well, don't I need to do exactly the same problem, except I want this now to be 300? All right, so see if you can go through those steps that we just went through, but you want your population now to be 300. Let's see if we can work through that on our own or with our partner. See if we can come up with the answer. Anybody have an answer yet? Which got Lauren?
11 days?
Oh, maybe. I probably did something wrong.
I don't know.
Let me try again.
Oh, I did it. I did 47 instead of 1.
Oh, okay. Braden?
About 17.
That's what I got, about 16.9, so about 17 days, the school's gonna close in about 17 days. All right, so let's talk about this, make sure everybody's with us. Anybody not get 16.9 and need to figure out what happened? Lauren figured out what happened with her, did you get it? Are we okay, people? know it tells us in the problem that there's 800 kids in the school, but even if they didn't tell us that, you should be able to tell from that equation. This is a logistic function. What's the limit to growth? What's the most kids that could get sick? 800, right? That's it. That's it. So there's 800 kids in the school. And that's the limit on keeping kids sick. All right, let's look at number 7. Are you ready? Number 7? 7, we're gonna do the same kind of thing, only now it's a population of deer. Speaking of which, they are out and about, you guys, so be careful. I don't know if you've seen them, but I have seen them every time I've been in a car this week. I've seen them this morning, right at the end of my neighborhood as I was turning off onto the main street. Huge big buck with big antlers.
You should have shot it, Miss Ford.
Should have shot it.
That's a good buck.
I think there's law against that, and I wouldn't even know how to shoot. Okay, all right, so here's our equation. Here's our equation. A, what was the initial population of deer? How did we say we were gonna do initial population always?
Is it 0? Plug in 0.
How do you find the beginning point? Anya,
Make T 0.
make t 0. Let x be 0. Find the y-intercept. Let x or t be 0. So think about it for a second, kids. If we plug in a 0, what's going to happen to this e thing? It's going to be 1, right? So we basically have 1,001 over 91. So the initial population is 11. That's my phone. It's probably some spam thing. I don't know how to make it stop. It's so frustrating. I know when it's done ringing, I'll put it back on silent. I forgot to do that. No one ever calls me except spam. I just get like 40 a day. I'm so tired of it.
You want me to start calling you?
No, it's okay. You don't have to call me. There's probably some more I can say to that. When will the number of deer be 600? So we start out, this population started with 11 deer. When is it going to be 600? Well, what do we do for that? Makes this 600. And then we're going to solve exactly like we did a minute ago. So go ahead and do that while I'm trying to figure this out down here. Go ahead and
You saved. Oh my God.
well, that's a good thing.
They'd be calling me at like 10.
That is, terminating one is a good thing. Can't you tell them to take you off the list?
I don't know.
All right. come up with an answer yet?
They got like 25.
24 and a half? Yeah, yep. So when will the population be 600? About 24 and a half days, or if you said 25 days, that would be fine. Is that okay?
Is it in years or days?
Oh, is it years? I'm sorry. Yep, it's years. I was gonna say that's pretty fast. I don't know what the gestation period for deer is, but yes, it's years. Thank you, Emma. I think I'm probably pregnant for more than a couple minutes. Yep, good. What is the maximum number of deer possible in the park? 1001. That's your limit to growth. So think about this population growth, or this population growing, but this is logistics. So there's an asymptote up here stopping it, and that asymptote's at 1001. Okay. All right. Good. Everybody okay with that one? We're moving on to number 8, which is exponential. Okay? It says in the directions, exponential. So stop and think about what do exponentials look like. They do not look like this. They look like a times b to the x. So your job is to write an equation for this. So the population in 1890 was 6250. So we're gonna let that be our initial value. That's where the population started being measured, in 1850, or 1890, so it's 1890. Assume the population increased at a rate of 2.75%. What is this going to be? What goes in here if this population is growing 2.75%? Anya?
0.0275.
Now, that, I want you to think about what you just said. Anya, what happens when I multiply something by 0.0275? Does it grow? It's gonna go down real fast. So 0.0275 is the correct decimal. But because my population is growing, don't I have to add it to 1? We always add or subtract our percentage from 1. 1 is the baseline. So 1 plus if it's growing, 1 minus if it is shrinking. Always. Okay? Now, estimate the population in 1915. Well, what was this? This was the population in 1890. So if we want to go to 1915, we would let X or T be 25. Does that make sense to everybody? We're waiting 25 years? And we just type it in. This one's easy compared to that last stuff we were doing. It is a people problem, so let's do round it off to the whole nearest whole person. So I think that would be 12,315. Is that what you got? Any issues there? So we're not going to do 1940. That would be exactly the same thing, except your exponent would be 50. Now, this is kind of a population growth problem, just like the deer thing that we did a minute ago. The difference is, does this equation have a limit? It's exponential. So it's going to just keep going, right? So these could be getting bigger and bigger and bigger. There's no limit on these. Logistic equations make you have a limit, boundary. All right, Predict when the population reached 50,000. So we're still using this equation, only this is next now. Predict when the population reached 50,000. Now, as always, Dan, we could do that by graphing, right? But we're gonna do it algebraically. So what will that setup look like? We're doing it algebraically. What do we do with the 50,000? Set it equal to, so 50,000 equals 6250, 1.0275 to the x. I thought that divided evenly. What's step one? Divide. Now, there's nothing wrong with leaving the fraction, but it actually divides in 8 times. There's nothing wrong. In our other examples, we left this. 5 over 147 or something. It's perfectly okay to leave it as a fraction. This one just happens to divide evenly. All right? Now what? That variable's an exponent. The only way to do it is to use logarithms, right? Now, last time I ln, could I ln again? Absolutely. I'm kind of a creature of habit, and if there's no e, I always log, but you can ln all the time if that's what you want to do. I'm going to go ahead and log both sides. Nothing cancels, but the exponent comes out in front. Oops. So when you take the logarithm of something to a power, the power becomes a coefficient. That's what makes the problem doable. It's not doable when it's an exponent, but it's not an exponent anymore. So now I can divide. Make sure, those of you that have older calculators like mine, when you hit log, it's going to put that parentheses in automatically, which is fine. Make sure you close it before you do divided by. So log 8, close parentheses, divided by log 1.0275. What was the question? When is it going to be 50,000? So remember, when did we start measuring? 1890. So X, I got about 76.65 years. But that's not the answer to the question. The answer to the question is add that to 1890. So it's going to be sometime in between 1966 and 1967. Is that what you got? That's the answer to the question. Everybody got that?
Wait, can you repeat that again?
So when I type this in, I got this. But that's 76 years from 1890.
That's not what I got when I tried to log 8.
Did you close your parentheses after the 8? Did you type 1.0275? I think I'm right. I'm looking at
No,
it.
I did too. I just don't. Now I got it. So then, wait, is the 76.5 or 76.65 your answer?
No. Your answer is start with 1890 and go that long. So it was like 1966. The question says when. So since we started in 1890, we got to use that as our base, that's our beginning, and then we add on to that. 9 on your own. It is exactly the same problem, exactly the same situation, different numbers. So see if you can answer the question. You're first of all gonna wanna write an equation, right? So let's see if we can come up with the right equation. Now, when you get your equation written, I want you to look up here and see if it compares favorably to mine. I don't want you just to copy mine down. You have to be able to write this equation on your own. It's exponential. We know the initial value, and we know we're growing 1.49%. So 1.0149. Any question about the equation? All right, let's answer the question then. Figure it out. Got to do the math to figure out when the population is going to be a million. I'm going to use ln this time just to show you that the answer will be the same.
We still do log.
Oh yeah, yeah, go ahead, still do log. I would do log under normal circumstances. I just want you to see it really doesn't matter. You can get the right answer either way.
Only log could bring that X down to be
And ln is a logarithm. It's a base C logarithm. Any logarithm will do that. Did you get about 20.73 years? So what's the answer to the question? When did we start measuring time? So it'll be about sometime in 2020. The population reached a million. Everybody good with that? Now again, I used ln. I normally would have used log. I just wanted you to see that it doesn't matter. You can use ln or log on any problem and get the right answer. We don't mix and match. Obviously, if you ln this side, you have to ln this side, but you could also log. Okay, we good on that one? All right, one more. The half-life of a certain radioactive substance is 65 days. There are 3.5 grams present initially. A says express the amount of substance remaining as a function of time t. Basically write an equation for this. Write an equation for this relationship. So I want you to think, what does half-life mean? Half-life means the time it takes to end up with half of what you had originally. Is that right? So if I start with 8 grams, by the time I get to 4 grams, that would be a half-life period, and then it goes down to 2, and then 1, and so on. You're looking at me like I'm from another planet. You did this in chemistry, people. I mean, you studied this. Half-life, radioactive elements decompose. They lose their radioactivity, and every certain amount of time, they lose half of it. That's called their half-life. That's how it's measured. All right, so we need to write an equation for that. Does anybody have a thought about it? Now, they tell me I'm starting with 3.5 grams. So my brain is going this direction, because that's an initial value. If I do that, what would have to be in here? What's my percentage? First of all, I'm not growing, I am decaying, so it's going to be 1 minus. And by what percent am I decreasing? 50%. So what goes in here? 1 minus 50%? Or 0.5? Now, I want you to think about this for a minute. If I think of this as the time. If I let t be 1, then that means after 1 day, I would have half of what I started with. That's what that equation says. Now, is that what's really happening in the problem? No. It takes 65 days. So how am I going to modify my exponent? It can't be a plain x or a plain t. I have to modify it so that I only get half every 65 days. Any thoughts on that? What? Not x plus 65. Think about this. Think about that for a second. Isn't every day 1/65 of a half-life period? Isn't it? So wouldn't it take 65 days to end up with half? So look, if you put 65 over 65, then it's 1, and that's what you want, right? 130 would be 2, and so on. So every day is 1/65 of your halving time, your halving period. So x days are x/65 of your half-life. Now later in the chapter, we're going to approach these problems a little bit differently, but right now this will work. Does this make sense to you? You are having, cutting in half, every 65 days. So if the half-life period were 17 years, we would divide by 17. Okay, that's the answer to A. When will there be less than 1 gram remaining? When will there be less than 1 gram remaining? What do you want to do with that? 1 goes here.
Would you ever change the sign? Since it's less
You know what, I could, Jake, but instead of messing with that, I'm gonna solve this, and let's say it comes out to be 10 days.
than.
I'm gonna say after 10 days, yeah, yep. All right. Okay, how do we solve it? Divide by 3.5. Now what? Log both sides. If you want, if your variables up here, guys, you need a log, or ln or something. You need to get a logarithm involved. So I'm going to log both sides. So the log of 1 over 3.5 equals x over 65 times log 0.5. excited, you can do this. Do we need to divide by the log of 0.65 or 0.5? The log of 0.5? So I can do that. So the log of 1 over 3.5 divided by the log of 0.5 will give me x over 65. So once I get that number, what do I need to do? Multiply by 65. So log 1 divided by 3.5 divided by log 0.5 times 65. Is this days or years or what? Days. So how many days is it gonna take? 117.47? About 117 and a half days. Would you agree? Everybody okay with that? All right, let's put our notes away. Let's just calm down here for a second. Put our notes away and grab a sheet of paper. And we're gonna practice a few exponent problems. Just to make sure that we remember all of our properties of exponents. We'll start with these four. Anybody have any idea how to do any of them? You better all know how to do them. Let's see, Lauren, what's your thought? Which one are you looking at?
First one,
Okay.
you subtract the exponents.
In a division problem, I subtract exponents, absolutely, but what? You can't do that unless the bases are the same. So, we can't, at this moment anyway, we can't subtract the exponents. However, there's something kind of special about 10 in terms of 5. Isn't 10 2 times 5? Would you agree with that? All right, now, when I have 2 times 5 to the 5th, that means 2 to the 5th and 5 to the 5th. 2 to the 5th times 5 to the 5th. Would you agree with that? They each go to the 5th power. Now, Lauren, I can cancel these because I can subtract the exponents because the bases are the same. So that's going to leave me with 2 to the 5th times an extra 5. You with me here? What's 2 to the 5th? 2 times 2 times 2 times 2 times 2. 32 times 5. The answer is 160. Could we have just on our calculator done 10 to the 5th divided by 5 to the 4th? Yes, but this is a no calculator exercise. So we gotta be able to do it without our calculator. And I could, without my calculator, do 10 to the 5th divided by 5 to the 4th, but it's gonna take forever, because those numbers are huge. So simplifying using the idea of exponents is perfect, but the bases, we can't do anything if the bases aren't the same. All right? We good? On number 1. All right, who sees another one up there? 2, 3, or 4 who you have a thought about? Katie?
2 just be 3 over x to the 3rd.
It would be very, very good. That one always catches some people, because you see the negative exponent and you know what to do. A negative exponent goes down. But only the thing with the negative exponent goes down. So 3 is 3. So it's 3 stays right where it's at, but the x cubed comes down. Okay? I love putting that question on tests and quizzes, because I just love tripping people up, and some of you get going too fast. It's 3 over x cubed. All right. Anybody know anything about these two? Nala?
And 7 squared over 6 squared.
That negative is going to turn this fraction over. Remember that? We talked about it earlier in the year. A negative exponent is 1 over, but if it's already a fraction, top comes down, bottom goes up. So the whole thing flips. So that would be 49 over 36. That one is very similar to this one. What do you observe about 4, 8, and 16? They are not random. 4, 8, and 16 have a very close relationship. What is it?
4.
Well, they can all be divided by 4, but in terms of bases, they're all powers of 2. 8 is not a power of 4. 16 is, but 8 is not. So I'm going to change all of these into 2's. So 2 squared to the 5th, 2 cubed to the 3rd, and 2 to the 4th to the 4th. Now take a look at that and see if it makes sense to you. Remember, I can't do anything with the exponents unless the bases are all the same. These are all very big numbers. I do not want to work all this out. So I'm going to do it in terms of their exponents. Everybody good with that? So what's this? That's 2 to the 10th times 2 to the 9th over 2 to the 16th. Perfect. What's this? 2 to the 19th over 2 to the 16th. Well, what's that going to be? 2 to the 3rd. So believe it or not, that mess just comes out to be 8. 2 to the 3rd. 8. No calculator necessary, right? Is that okay? All right. What about this one? Okay, what about this? What's going to happen here? Nyla?
It's going to be 2 times 2x to the 4th over x to the 4th.
So this guy is going to come down, but this whole shebang is going to go up. So she said 2, and then 2x to the 4th, because that came up, over x to the fourth. And then what happens with quantity 2x to the fourth? That's gonna become what? 2 to the fourth is 16. Oh my, what's the answer to the problem? 32. Digest that. That makes sense to you? What happens with this? What's going on here? First of all, see that negative? What's that gonna do? Turn it over, it's gonna be 9/16 to the 1/2. Oh, 9x to the 16. 9 over x to the 16. What's 1/2 mean? Square root. So 9 to the 1/2 is 3. And then be careful here. We don't square root 16. This is a double exponent. What do I do with those exponents? Multiply. So this is x to the 8th. If you square x to the 8th, you get x to the 16th. Never square root an exponent. Cut it in half. Don't square root. All right, I got 2 sets of problems. This one looks a lot like the one over here that we just did. So we're gonna have 5 x cubed is coming down and 5x cubed is going up. Would you agree with that? Guys? Yes?
Yeah.
Got it? Okay, so that's 5 times 125 x cubed. Remember, that's a quantity, so 5 cubed and x cubed. So 125 times 5. 625 is my answer. Because the x cubes cancel. You okay with that? Kara, you all right with that? All right, what about this one? We already did one like this, talked about it. What are we gonna have to do if we're gonna simplify this without a calculator? Break down 10, leave 5 to the 5th alone, and then 10 is gonna be 2 times 5. So that's gonna be 5 to the 5th on the top, and then 2 to the 4th, and 5 to the 4th on the bottom. The 5 parts I can simplify. So there's 4 here, 5 there. So 5 over 2 to the 4th, which is 5 over 16. Quickly, we're almost out of time. What's that? That's my tricky, but no one's gonna fall for it. It's 2 over x squared, right? 2 over x squared. How about this one, last one? 16 to the 4th over 4 to the 5th times 8 cubed. Make them all powers of 2. So 2 to the 4th to the 4th. 2 squared to the 5th, 2 cubed to the 3rd. Two to the 16th, 2 to the 10th, 2 to the 9th, this looks familiar, 2 to the 16th over 2 to the 19th, what's my answer gonna be? 1 over 2 to the 3rd, which is 1 over 8. I don't wanna pop anything in on you, so I'm gonna tell you straight up, tomorrow we're gonna have a little quizzy poo, we have sheet of paper, we'll practice some of these exponents, okay? They'll be just like the ones we just practiced. So if you need to practice again, write down the problems on another sheet of paper,